All right, last concept we're going to talk about as part of section 3.4 is points of inflection. So points of inflection, the definition of points of inflection are the points at which the graph changes from concave up to concave down, or from concave down to concave upward. So they're points at which the concavity changes. Right? The way we find them is to look for places where the second derivative either equals 0 or does not exist. Right? These are possible points of inflection. They're not automatically points of inflection because either one of these things is true. We may have a vertical asymptote at which the second derivative wouldn't be defined. We could have some kind of fairly unusual, but a function such as y equals x to the fourth is a good example of when you find the second derivative instead of equal to 0, you get x equals 0 as a possible point of inflection. But when you look at the concavity on the left and the concavity on the right, they're both concave up, so that's not really a point of inflection. So when we do that, when we try to claim that something is a point of inflection, first of all, the point has to exist, and secondly, we have to show that the concavity changes from positive to negative or from negative to positive. So that's a really important point. Just showing that the second derivative equals 0 does not make that point a point of inflection necessarily. So we're going to go back a little bit now and talk about relative maxima and minima. All right? I would call this a sometimes simple test for relative maxima and minima. If we use the first derivative test in order to show a relative maximum, we needed to show that our first derivative, so f prime, went from positive to negative for a relative max. And for a relative min, we needed to show that f prime went from negative to positive. So we had to have a change in the sign of the first derivative. Another way another way for us to show a relative maximum or minimum is to use the second derivative test rather than showing this transition from a positive first derivative to a negative first derivative. So if the second derivative exists at this point, and we have a relative extrema, then we can look at the second derivative. If the second derivative is positive at that point, then we have a relative minimum. And if the second derivative is negative at that point, then f has a relative maximum. And we can think about that in this way. If I have a point with a critical value, and I have a positive second derivative at that place, that means that, if we have a positive second derivative, then at that point the function has to look like that. It has to be concave up at that critical value. So if that's true, then we must have a relative minimum at that point. And then if the second derivative is negative at that critical value, that means that in that area we have to have a concave down function, which means we have a relative maximum at that point. So the reason this is sometimes simple is for functions where it's very easy to find the second derivative. So if I have the first derivative and finding the second derivative is very simple, then to use this test I only need to find one second derivative. So I find the second derivative quite easily, and then I plug in the actual c value and I just have to evaluate that second derivative once. Whereas if I use the first derivative, I have to evaluate the first derivative on the left and then evaluate the first derivative on the right. So if the second derivative is easy to find, oftentimes the second derivative test is useful and helpful.
Hammett, if you're in the building, please come to the front office. Fern Hammett, if you're in the building, please come to the front office straight away. Thank you.
All right. So if you notice here that if the second derivative is greater than 0 or the second derivative is less than 0, we have a minimum or maximum respectively. But if the second derivative turns out to be 0, then the test fails. So if the second derivative at our critical value is equal to 0, then we don't know whether it's a minimum, maximum, or neither. So if that's the case, then we have to go back and use the first derivative test. So we have to go back and look at the first derivative and look at whether it goes from positive to negative or negative to positive, and then make our determination of whether we have a relative minimum or maximum.